This final script for week 1 of Math 23 deals with the two applications discussed in subsection 111 of the executive summary. These are two cases where matrix multiplication is relevant to the problem and provides a nice way to organize the computation, even though the interpretation of matrix as representing a linear transformation doesn't fit so obviously with the example. Our first example is what is called by probabilists a Markov process. A Markov process involves a system that can be in one of two or more states and that makes transitions from one state to another in accordance with specified probabilities. Our example is a game of volleyball. In volleyball and other similar games, the team that's on serve continues to serve if it wins the point, but if it loses the point, then the serve passes to the other team. We can characterize the situation in a volleyball game in terms of the probability that team 1 is serving and the probability that team 2 is serving. And the problem we're going to try to solve, though we can't do it completely with what we just know about matrices, is to figure out the answer to the question, if we walk in late in the game, what's the probability that team 1 is on serve? So first let's think about what our vectors mean. Here's a vector v0. First component is 1, second component 0. That means the probability is 1 that team 1 is serving, 0 that team 2 is serving. And you can see the only vectors that make sense in this context are vectors that can represent a pair of probabilities. Both entries are between 0 and 1, and their sum has to be 1. I will set up a screen with as much space as I can get by making the margins very small. And since the horizontal axis refers to the probability that team 1 is on serve, the vertical axis to team 2, I will use labels team 1 and team 2 to go along with the two axes. Now I've drawn a line that goes from 1, 0 to 0, 1. That red line segment in between the axes represents all possible points or vectors, you can think of them even either way, where the sum of the two components is 1 and both of them are positive. We have a function, little f, that updates our probability vector. Basically, it takes the probability vector before a point is played and converts it into the appropriate probability vector for after a point is played. If before the point team 1 is sure to be serving, then, assuming that team 1 has an 80% chance of winning the point and retaining the serve, the probabilities after that point are 0.8 for team 1 on serve, 0.2 for team 2 on serve. We can also assume that team 2 is likely to retain the serve, but it does so with only a 70% probability. So if we start with team 2 definitely serving, there's a 30% chance that team 1 will be serving after the point. We can capture all this information in the matrix capital F. The first column tells the probabilities of team 1 on serve and team 2 on serve, assuming that team 1 was serving before the point started. The second column gives the corresponding numbers for the case where team 2 was on serve. If team 1 is definitely serving when we start out, we can represent the starting situation by that horizontal blue vector, and now we play the first point. How do we update the probabilities? Well, the probability of ending up with team 1 on serve is the sum of two terms. The probability of their being on serve times the probability conditioned on their being on serve that they retain the serve, plus the probability that team 2 instead was on serve multiplied by the conditional probability that the serve passes over to team 1 because team 2 loses the point. Matrix multiplication does precisely that calculation and turns our vector into a vector v1. So after 1 point has been played, there's an 80% chance that team 1 is still on serve. Now we play the second point. And when we do the calculation, now we use the fact that there's a 20% chance that team 2 is serving, but it's still the same calculation. We multiply the matrix F by the vector v1, and we get a vector v2 that represents the situation after 2 points have been played. Now we multiplied the vector v0 twice by F. Because matrix multiplication is associative, we could have done the multiplication first between the two copies of the matrix F. So I have made F times F, called that a matrix F2. That's a matrix that updates for 2 points. And if we apply that to V0, it gives us the same result, of course, as if we used F twice in succession. Now if we've played 2 points, we can update by F2 to figure out the probability after 4 points have been played. There it is. Or we can square the matrix F2 to get a matrix that updates for 4 points in one fell swoop. We can even easily create a matrix that represents the effect of 4 more points. And now if you looked at this, you may have made a conjecture. You may have said to yourself, it looks as though those blue vectors are converging to something, that there's some limiting vector. And in fact, if you look at the numbers, you might guess that that limiting vector is 0.6, 0.4. An interesting way to check that is to ask, suppose we had those probabilities, what would be the effect of 1 more point? Multiply by F, and the answer is the vector stays the same. That means that late in the game, we expect that the probability that team 1 is serving will be 0.6. This vector v limit is technically known as an eigenvector. It's an eigenvector with eigenvalue 1 for the matrix F, which means that the effect of the matrix F is to multiply it by the value 1. In week 4, we will look in detail into this subject of eigenvectors and eigenvalues, and we'll revisit this problem. Second example is very similar to one in the textbook. It involves a collection of islands where one can travel around on ferry boats, and I've drawn what computer scientists call a graph to represent the situation. The islands 1, 2, 3, and 4, are said to be nodes or vertices of the graph, and the ferry boat routes are edges of the graph. By drawing arrows, I can indicate that from island 1 you can get to island 2 or to island 3, but not to 4. And I can capture that information in a vector that has a 1 for each of the islands that can be reached by a ferry ride from island 1, a 0 for the 2 that cannot. I can do the same thing with island 2. You can go from island 2 only to island 4, but not to any other island. That's represented by a vector that has a 1 in the 4th position. From island 3, we can go back to island 1, or we can go to island 4, but there's no ferry boat that goes straight from 3 to 2. And finally, from 4, you can go back to island 1, but that's the only possible journey. Now let's put those 4 columns that represent the ferry routes out of the 4 islands together to make a matrix. What's the meaning of the square of this matrix? Well, you can argue if you start on island 3, let's say, multiplying once by the matrix A says you can either be on island 1 and on island 4, and then you can follow up the root out of island 1 and island 4 by multiplying again by the matrix A, and the matrix A squared gives us the number of two-boat ride journeys from each island to each other island. In this case, it's fairly easy to check. Let's look at the first column. Starting from island 1, we can go to island 3 and then straight back to island 1. So there's one two-path route from 1 to 1. If we want to go from island 1 to island 4, there are two routes. We can go from 1 to 3 to 4, or we can go from 1 to 2 to 4, and matrix multiplication has got that correct. There's a 2 in column 1, row 4. Square again, we get the number of four-step paths. And now this becomes actually quite difficult to check by hand. It says correctly that there are 3 ferry boat journey paths that take us from island 3 to island 1. It took me a while to find all 3 of them. They are 3 down to 4, across the diagonal to 1, over to 3 and back to 1, 3, straight back to 1, down to 2, over to 4 and up to 1, and 3 to 1, back to 3, down to 4, up to 1. So here's a situation where the matrix multiplication isn't of profound mathematical significance, but it is a very convenient way to organize the computation. And if you get into studying computer science, you will discover that so-called adjacency matrices or transition matrices like this are a standard way of representing the graphs that play an important role in computer science. We are done with this script. We are done with the material for week 1.